This is section 3.1, sampling from a finite population. You'll find when we do this that a lot of it will feel like a review from chapter 2. Okay. In this textbook, they're doing a spiral approach. So we learn a topic, and then we kind of learn a new topic, then we review the old topics, and we just kind of keep learning and reviewing and building one little detail at a time. Okay. And that's why you'll often feel like we're kind of reviewing again. So we are going to do a lot that feels like a review, but there's also some new things in here, so make sure you don't fall asleep because it sounds familiar, because some of this new stuff is very important and will be on the exams. So look at the learning objectives. This comic is very pertinent to our lesson today. Okay, when it says the king is conducting a survey, how do you feel about paying taxes? And the guy says, well, I can't complain because there's a guy that's going to club him if he does complain. Okay, so this is a type of bias that can be introduced when we're influencing people's results on surveys, which we're going to talk about in this lesson. Okay, but first though, a few things about categorical variables. Okay, bar graphs, we said if we have categorical data, we can summarize the data with proportions and with bar graphs. Okay, now just to be technical here, on the horizontal axis of a bar graph, you should put the actual categories of what you're measuring. And on the vertical axis, you can put the count or frequency or percentages or the proportion of data in each category. So for example, let's say we collected data that at USU, 41.9% of students are age 18 and 21. Okay. So what was the variable here? What were you actually asking people? And you're going to find we're going to ask you this for the entire semester. We're not going to stop asking it because it is so important that you figure out what kind of variable is it. Is it categorical or quantitative? The reason why is based on your answer, then that's how you choose what you need to do for the rest of the problem. Okay, let's see. So it does kind of look like we looked at age, but if you're looking very specifically, it says 41.9% of students are age 18 to 21. So that sounds to me like they asked them, are they 18 to 21 or not? Okay, so this was very much a categories. They had two categories here. Anytime they give you like a percentage of people that did something, that was going to be categories. So the variable is whether they are 18 to 21 or not. Those are the two categories. So it is categorical because there are only two categories. It's also, you could be more specific and say it's binary, which means we can use proportions or percentages to summarize it. Okay, so what is the proportion of students age 18 to 21? Well, it said 41.9%, so that would be 0.419. Now let's create and label a bar graph. Okay. This is something that is new. We didn't ask you to do this before. We just showed you it, the bar graphs after they're made. So you could say, here's the 18 to 21 is one category, and then the other category would be not, or maybe they wanted to call it older or whatever you want to call it. Okay, but you have age 18 to 21 or not. Okay. Now let's see, we have a proportion of 0.419 that are that. So let's make one graph that goes up to 0.419. And then the not older, how high do I need to make that? If I did 1 minus 0.419, that gives me 0.581. Okay, so this is for the people that are not. So we need to go up to about 0.581, and shade it in if you want, just to make it a little bit prettier. There's your bar graph. You can see that there were more people that are not age 18 to 21. Okay, when you make these bar graphs, I don't really care if it's to scale. We're not being that specific. I just want to know, like, do you understand the overall concept? On the exam, I could ask you, like, what labels should be on this horizontal axis, or which bar graph seems like it matches this data. Okay, this next part is going to seem like a review, but we're going to throw some new information into. So let's review our populations and samples and the central limit there. So remember, your population is the entire group of individuals that we're interested in. Your parameter then is a number that summarizes that population, or maybe it was actually a random process, not a population of people. Your sample is a smaller group of that population that you actually collect the data on, and your statistic is a number that summarizes the data that you collected in your sample. So back to our example, at USU, 41.9% of students are age 18 to 21. So the population would be all USU students. The parameter is the proportion of all USU students that are 18 to 21. Now that's how you write it out in words. We often don't know the parameter, and so we just write out in words. But I could also write it with symbols because it did tell me the parameter. It told me how many USU are at that age. It's 0.419. So that would be the parameter. We use a pi for the parameter proportion or population proportion. Now let's say we want to take a sample of 40 students to see what percent are age 18 to 21. I took one sample and found that 30% were in that age group. Okay, so my sample, or what was my sample, it would be the 40 USU students that I actually collected data on. And the statistic would be the proportion of students in the sample that are 18 to 21. Okay. And what would that be in symbols? Well, for your sample proportion, we do this p hat, and it is 0.30, so we said 30%. So our sample proportion that we got at 0.30, that's actually a lot lower than our population parameter of 0.419. I'm like, I wonder if I did something wrong. Maybe, maybe not. Okay. But it does seem really low. So maybe we should take more samples and see what happens. Like maybe that's completely common. All right. Very plausible. So if I take more samples, I use the computer and I found more samples. So on my first sample, I got a sample proportion of 0.30. On my next sample, I got 0.35. My next sample, I got 0.35. And you can just see, etc. I took 20 different samples, and these are the different sample proportions that I got. And so you can see that each of my different samples gives me a different sample proportion. Okay. This is called sampling variability. The idea that each sample gives you different results, very, very important. This is what underlies all the statistics we do in this class. Okay, so some of our sample proportions, p hat, are going to underestimate the population proportion. So like our true population proportion is around 0.4ish, right? So everything over here is underestimating it. Everything up here is overestimating it. Okay, but some are closer than others, and we kind of hope in the end that if we took lots of different sample proportions, that they'd average out right at our parameter of 0.419. Okay, so I can't tell you if you go to take one sample, if you're going to be overestimating or underestimating, if you're going to be really close, if you're going to be farther away, but I can tell you the overall behavior of all the different sample proportions. So now I use the applet to take thousands of samples of size 40. So I'm to the ISI applets categorical in one proportion. I put in 0.419 for my probability of success. 40 is my sample size. I asked for 10,000 samples. And I did proportion of successes versus the count or the number of successes. Okay. And it gives me this nice graph. I click some summary statistics so I can see my mean and standard deviation. It tells me here are the proportion of successes. Now, if I'm looking at this label, this should really say the proportion of successes in all the different samples, right? So each one of these like individual dots, there's 10,000 dots, so you can't see the dots anymore, but each of these little dots would represent a different sample. So it's the sample proportion in the different samples. Okay, let's see, where does that distribution seem to be centered? If I was going to guess where it's centered, I'd probably say about like right here-ish. Okay. You might have noticed I switched my value, so let me pause and fix that. Okay, now that I fixed my little issue of typing the wrong number, okay, let's see, coming back to it, when I asked what's the more accurate label for the graph above, we probably want to say something like, it's the sample proportions for each of the 10,000 different samples. That's even better than what I said the first time. Okay, now we asked where does it seem to be centered? I would say your center is probably like right about here. So about 0.4-ish. Hard to tell exactly from our graph. Let's see, what is the shape? I would say it looks pretty normal. And if we want the mean of all of those different sample proportions, we can just look right here. It will tell me if I click the summary statistics box. And also make sure that if it asks you like what's the mean of the proportions, that you're on proportion of successes and not the count or the numbers of successes. Okay, so my mean is 0.419. and my standard deviation is 0.078. Okay. So you notice that my mean of all the sample proportions is 0.419, and if you remember, our population proportion is 0.419. Again, not a coincidence. Okay. Now, of course, that was only, it was actually over 100,000 different samples when I did it the first time. Okay. Since I already did it, there's only 10,000 samples. Okay, but you can see that it still lined up with what I was expecting to get. Okay, but theoretically, we could take millions and millions of different samples. So the distribution of all the possible sample proportions is called the sampling distribution. Okay. And there's a note later in this that we'll talk about. So if you know your population proportion and you're looking at the distribution of all the possible sample proportions, it's called the sampling distribution. When we're doing hypothesis testing, our book actually calls it the null distribution. It means the exact same thing. It's just they called it the null for the null hypothesis. The central limit theorem, so this part is a review from section 2.5, says for a large population, as long as the sample size is big enough, remember at least 10 successes and 10 failures in each sample, then for all the possible sample proportions, the sampling distribution will have, the shape will be normal as long as your sample size is big enough. The mean of all the possible p-hats will just be equal to pi, our population proportion, so in our case 0.419. And the standard deviation of all the possible p-hats, we could write like standard deviation of all the p-hats, is going to be the square root of pi times 1 minus pi over n. So square root of 0.419 times 1 minus 0.419 divided by our sample size, which in this case was 40. Now, to put this into your calculator, you do need to be able to put it into your calculator. I like to do in a lot of steps. So I do 0.419 times, and I do the parentheses 1 minus 0.49 parentheses. I hit enter. Then I divide by 40, hit enter. Then take the square root of all of it. So basically all of this, top and bottom, has to be inside your parentheses. You have to love technology. So we get 0.078. So notice my theory base matches up exactly what I got when I did my simulations. Okay. And so if you forget to do these calculations on the exam, or your calculator just isn't working, you're hitting the wrong buttons, or you just don't want to mess up, or you want to double check your work, just go to the simulation. As long as you're doing at least 10,000 samples, your answer is going to be so close that you're going to get the right thing on the exam. Like you might be off a little bit by rounding, but we'll make sure that that rounding doesn't affect you on the exam. Okay. Now, here's the important new part. So when the mean of our sample proportions, okay, that average of all the different sample proportions we got, when that is equal to the population proportion, then our sample results are unbiased, which is very important in statistics. It means that on average, our estimates aren't overestimating or underestimating the population parameter. So like if you were to look at our different samples, sure, some of them underestimated it and some of them overestimated it, but on average, they were right on. Or you could say that because our distribution of sample proportions seems to be centered around the parameter of 0.419, it's unbiased. Now, on the other hand, we would say our sampling method is biased. The way we're taking our samples is biased if our estimates are consistently over or under the population parameter. So when we used our simulation, it was always picking random samples, and random samples are unbiased. And so our means did match up to what they were supposed to. But if we are picking our samples a different way, they might actually be biased. What we have to do in statistics is make sure we pick our samples in a way that they stay unbiased, so they don't overestimate or underestimate. Now, this next section is called finite populations. This is why the whole review was in here. So basically, all of our formulas for everything we did was based on an infinitely large population. In practice, all the populations we're interested in are finite. Like there aren't infinitely many people on this earth to survey. Okay? But usually our populations are going to be thousands or millions of items or thousands of millions of repeated processes. Okay. So we use this formula for the standard deviation p-hats as pi times 1 minus pi over n. And you take the square root of it. Well, that formula only works for an infinitely large population, theoretically. But the formula still works really well if the population is large compared to the sample size. Okay, so the rule of thumb is usually your population needs to be at least 20 times larger than the sample. Then all of the formulas work nicely. Okay. And so that's just kind of a little technical note. Doesn't really affect you. Our populations are always going to be really big. Okay. And so the difference between the theoretical and having a not infinitely big population doesn't really affect any of us. Like the decimal point, it would be rounded off so far down that no one ever cares. Okay. Now, also to note though, as long as our population is at least 20 times larger than our sample, it doesn't matter how big the actual population is. It doesn't affect any of our calculations. So you can think about it as if you have a huge bucket of water, okay, or like a small bucket of water, but let's say it's the exact same water. If I take a cup of water out of this one, or the same size of cup of water out of this one, it doesn't actually affect how good my estimates are, okay? So the cup from this estimates just as well as the cup from this. Okay? Or in other words, if I take a sample of 100 people from a small population or a sample of 100 people from a big population, my samples are going to be just as accurate because they're both 100. Okay, or in other words, the population size never shows up in any of our calculations. It doesn't matter how big the population is, as long as it's at least 20 times bigger than the sample. Okay, so part of the new part for today is good and bad types of sampling. Okay, we're going to talk about sampling bias. So if we don't use a good method to pick a sample, we get what's called sampling. So sampling bias means that we will consistently overestimate or underestimate. So we're going to either consistently overestimate or underestimate. But whichever one it is, we're going to consistently do the same thing. And that's bad. We don't want that. This is called sampling bias because it's based on what kind of sample we used. So little note, the sampling frame is the list or group of people we're actually picking the sample from. We want to make sure that our sampling frame actually matches the population. So theoretically, we should be picking from the entire population. But sometimes people don't do a good job of picking a sample and they're actually using a smaller sampling frame that doesn't match the population. So let's think about how I could take a sample of 40 students at USU. For each scenario, do you think the proportion of students who are 18 to 21 will be higher or lower than 41.9%? So let's say I walk into some USU 1010 classes. Now that's a class that's taken by students their first semester and sample 40 students. Okay. So, well, let's think about this. If we only go into USU 1010 classes, I would bet most of the students, those are all students in their first semester, so most of them are probably going to be 18-year-olds. So I would actually bet that our percentage will be a lot higher than 41.9%. I would bet that almost all are 18 to 21, mostly 18. So we are going to be overestimating by a lot. And the problem here is that I didn't look at all students at USU. I only looked at students in this one type of class that's only for mostly 18-year-olds. Okay. So let's try a different approach. Let's say I find some graduate level classes and I sample 40 students. Well, the sampling frame, I'm only looking at graduate students. Graduate students are usually older than 22 because they've already done 4 years of college. So if they're older than 22, then we would say like almost all are over 21, which means not very many are 18 and 21, so we're going to be underestimating. Let's say we want to sample 40 of your friends. Well, the sampling frame then is going to be your friends, and they're probably similar in age to you. So if you are a concurrent enrollment student, most of yours are going to be high school, so you're not going to be in that 18 to 21 age range. Or if you're in my college students, some of you might be 18 to 21, and your friends are probably 18 to 21. Okay? But some of you might be older, and then your friends are probably older as well. So that one just kind of depends on your situation. Are you younger or are you older? Okay, but either way, it's probably not going to be accurate. Let's try this next one though. I get permission to get a list of every student at USU and randomly sample 40 students from the list. The sampling frame then is going to be every student at USU. So I write down the list of every student at USU. I have a computer pick out 40 students for me randomly. That should give me really good results. It will be unbiased. So to review, the sampling frame is the list we're taking samples from. We want the sampling frame to contain every member of the population. If I'm interested, if I say my population is USU students, I need to actually sample from all the students at USU. I don't want to just look at USU 1010 students, I don't want to just look at graduate students. I don't want to just look at your friends. I want to look at all the students at USU and randomly pick some. It's unbiased if the average of all the possible sample proportions is equal to the proportion pi. So that meaning that on average, we're not overestimating or underestimating. Bias means we consistently overestimate or underestimate the population parameter. And we don't ever want anything to be biased because then we know our results are off. Here are some examples of bad types of samples that would be biased. Okay, the first one is convenient sampling, which is very common because it's very convenient. Its subjects are chosen because of their convenient accessibility to the researcher. So the subjects are selected just because they're the easiest to recruit for the study. The convenient samples are almost never representative of the general population. So some examples of convenient samplings would be like sample 40 of your friends, or sample the first 10 customers who walk into a store, or sample 20 people in your class, or sample 30 people at the TAC when you get there. Those are all convenient, easy samples, and they're usually going to be biased. The next thing is called a volunteer response sample. This applies to all like mail-in surveys, call-in surveys, online polls. It's where you let people volunteer to be in the study. Volunteers are often different than the general population. We find that people who feel strongly towards an opinion are more likely to volunteer to be in a study. They're even more likely if they have negative opinions. People that are really busy are less likely to volunteer to fill out the survey. So if you take out everyone that's busy, then you're cutting out a huge portion of your population. Volunteers also often feel differently about the issue than the general population. And so volunteer response samples are always going to be biased in some way. So what we want to do is we want to use random samples. In this class, we're only talking about simple random samples, which is the most simple. They're always unbiased, which means they're very good. So random samples mean we let a random process choose the samples. There's no human choice at all. So for example, you could write a list of everyone in the population, assign each one a number, and have a computer randomly generate numbers, and those are the people that you go sample. Random samples are unbiased. There are lots of different types of random samples for various scenarios that can get very involved and technical. In this class, we only talk about the simplest version, which a simple random sample is when every person in a population has the same chance to be chosen. If we have unbiased random samples, then we can generalize the results from our sample back to the larger population. That means that we can say the results from our smaller sample are probably true for the entire population, and that is our whole goal in statistics. So we want to make sure we have good samples. Now, there are other types of bias that you can have besides how you pick your sample. It's called non-sampling bias, and there's a lot of different ways that this can show up. Some examples are you pick people to be in your sample, but they refuse to participate. That's called non-response. Not that you have to remember that one, but you might see it as you read articles. It's non-response bias. You might have misleading questions. Maybe people are embarrassed to answer honestly. Sometimes people forget or they overestimate or underestimate their answers. Like I probably overestimate how much I actually exercise in a week or underestimate how much sugar I eat in a week. Okay. Or interviewers might purposefully or unintentionally influence the answer. So remember back to our comic. Okay. The interviewer was definitely influencing the answers. Okay. If you're interested, here are some interesting articles about the 2016 and 2020 elections and how the polls gave misleading results because they were very misleading. So like for 2016, the article suggests a concern such as non-response bias. That's when you pick people but they don't respond. Or that maybe pro-Trump people had viewpoints that made them less likely to respond to the surveys. Maybe there were shy Trumpers, people who were unwilling to admit that they wanted to vote for Trump because they were that embarrassed about it. There's also a video on this same page as the video you're currently watching. If you prefer to watch the video, then read that article. So this is going to seem like we're still reviewing. There are a couple new points though that you might see show up on the homework or exam, so make sure you're still paying attention. So we're kind of reviewing the central limit theorem and our sample sizes. So in the 1860 presidential election, Douglas got 21% of all the votes. We want to take a sample and see what percentage of people voted for Douglas. So let's see, what is the population? The population was all the 1860 US voters. The parameter would be the proportion of all 1860 voters that voted for Douglas. And in this case, do we actually know what that value is? We usually don't know the value, but in this case, because it was a historical election, we can tell you it was exactly 0.21. That was our population proportion. Okay, what is the sampling frame? Like, did we actually look at all the voters? Well, in this case, I can tell you that it was all the 1860 voters. So they didn't, by that I mean they didn't just look at the people in Rhode Island. They didn't just look at the people in Maryland, or they didn't just look at the Democrats or just look at the Republicans. They actually looked at everyone. So that's what we're hoping for. The observational unit would be each voter. The variable of interest, well, what did they ask them? What was the question? It was whether or not they voted for Douglas. Now, really, they probably asked them who did they vote for, but all that we actually recorded for this specific example is whether or not they voted for Douglas, and that would be categorical. So I had the computer find theoretical sampling distributions for sample proportions of different sizes. So you can see these are the samples of size 20. It seems to be centered around that 0.21. Right here, like 0.21, that's where it's centered. If I do sample sizes of 40, it looks like we're still centered at 0.21, and sample sizes of 400, we're still centered at 0.21, which is good because that was our population parameter. Okay, if I look at the standard deviations though, what do you notice? As my sample size got bigger, my standard deviations seem to shrink, right? What this tells us is bigger samples give you more precise results. Bigger samples have less variability. Okay. Also, as you're looking at it, what happens to your shape? So when we first started at 20, were we still a little bit skewed? I feel like we're still a little bit skewed to the right. Okay. By the time I get to 40 though, like I don't really even see any skew. I'd say I'm pretty normal. And by the time I get to like 400, I mean, it's really skinny because I kept them all on the same scale, but I would definitely say it's normal. I don't see any skew at all. So let's write these notes down on the next page. As the sampling size gets bigger, the sampling distribution of all the possible proportions gets, well, my shape gets more normal as my sample size gets bigger. My mean stays at 0.21. And remember, that's important because my population proportion was 0.21. And my standard deviation got smaller. So bigger sample sizes have a smaller standard deviation of the possible sample proportions. Let's see, so all of the sample sizes are unbiased because they're all centered at pi equals 0.21, so that's good. What sample size gives you the most precise results? Or which sample size is giving you estimates that are consistently closest to 0.21? Well, if you look at it, like at a sample size of 20, I might get 0.21, but I might also get like 0.5 or 0 or 0.1. When I get to sample size of 40, I might be 0.2 or 0.1, 0.05, 0.4, but I'm getting a little bit closer to 0.2. By the time I get to sample size of 400 though, notice I'm only going to be between like 0.1 and 0.3. Like there's really not any other options. Okay, so at a sample size of 400, we're consistently the closest to 0.2. So 400, or the biggest sample size, gives us the most consistent results. So if I was to use a sample size of, say, 40, let's just pick one, how much sampling error can we expect? When we say sampling error, we're like, how far off is our sample from our sample statistic from our population parameter? Or what's the expected amount of sample-to-sample variation in the sample proportions? If I ask you anything like that, I'm just asking you, well, what is the standard deviation of the p-hats? Okay, you could just look up at the graph, but let's go ahead and practice calculating it. So this is copied from my old notes. These say p's. They should say pi's. Believe it or not, I have proofed these notes like 3 or 4 times, but you just miss things because you're used to seeing it. Okay, so our pi was 0.21, and then 1 minus 0.21, all divided by 40. So remember, to put this into your calculator, you need to do 0.21 times 1 minus 0.21. Hit enter. Divide by 40. Hit enter. Then take the square root of all of it. You should get 0.0644. Let's see if I did that correctly. Let's go back up to our graphic. At a sample size of 40, my SD was 0.065, so they just rounded differently than I did. So that's about your expected amount of variation from sample to sample for what you'll get for your sample proportion. Now, it turns out that there were over 4 million voters in the 1860 election. That's definitely finite, it's not infinite. But is it enough bigger than our samples to treat it like an infinite population and use our formulas? So basically, is it 20 times bigger than our samples? Well, definitely, for sure, okay, because like 20 times 400 is still going to be 8,000. Okay, it's easily much, much, much bigger than our samples. So, yes, okay, it's definitely big enough. We don't have to worry at all. Now, for the central limit theorem to kick in and guarantee that the sampling distributions will be normal enough to use our theory-based normal curve instead of using simulations, we need at least 10 successes and 10 failures in each sample. So which one of our sample sizes is actually big enough to use the central limit theorem? Now, in this case, we don't actually have a sample. So previously, when I've asked you, is it big enough, you actually had a sample. You can say, in my sample, there were this many successes and this many failures. But we don't have a sample at this moment. This is all theoretical. So I can't tell you how many successes and failures I got. Okay? But we can look at how many we expected. So we need, oh wait, I guess it's written right here. We need at least 10 successes and 10 failures. So let's look at how many we expect. So if my sample size is 20, we would expect, okay, so how do we do this? If you have a population proportion of 0.21 and your sample size of 20, what is like 0.21 of 20? Wouldn't you expect about 0.21 of 20 to be a Douglas square? So we want 0.21 of 20. If you think back to your math classes a long time ago, if you want to do 0.21 of 20, you just multiply. So 0.21 times 20, sorry, 0.21 times 20 gives me 4.2 successes. Okay. And if you want to figure out how many failures, there's two ways. You could just subtract this from 20, or you could do 1 minus 0.21 times 20, which gives me 15.8 failures. Or you could just do 20 minus 4.2 and you'll get 15.8. So in this case, is this one big enough? Well, the failures is big enough, but my successes is not. So 20 is not big enough to use the normal curve. Okay, let's try 40. So we would expect, let's see, 0.21 times 40 gives me 8.4 successes. Well, that's already not big enough, so we would say no. Okay, for 75, what will we expect? We can do 0.21 times 75 gives me 15.75 successes. But you can't check just your successes. You always need to check your failures. So I can do 1 minus 0.21 times 75, which should give me 59.25 failures. So if that's big enough at 75, then 75 is big enough. And really, if 75 is big enough, is 400 also going to be big enough? Well, yes, but let's just double check. We could do 0.21 times 400 equals 84 that are going to say yes, and 1 minus 0.21 times 400 should give me 316 that said no, or you can call them successes and failures. Both of those are at least 10, so yes. So basically we have this dividing line. 40 or less was no, 75 and above was yeses. Now, on a separate note, let's look back at the sampling distributions on our previous page. For what sample size are you least likely to get a sample with a p-hat of 0.35? So let's just look back up here without doing any math or anything. We want to see, will I get a sample of 0.35? So for sample size of 20, 0.35 is right here. That seems fairly likely. For a sample size of 40, how likely are we now? Like, I can still do it, but I'm a bit less likely, right? But at a sample size of 400, are you going to get a sample proportion of 0.35? It looks like it'd be almost impossible, right? Like, there's no other samples that went that far out. So, coming back to this one, for what sample size are we least likely to get a sample with a proportion of 0.35? So, least likely would be sample size of 400. Okay, so now let's use our applet, our eyesight applet under the categorical, the one proportion applet that we've been using, to actually estimate the probability of getting a sample with over 35% Douglas voters. For which sample sizes was the theory-based normal curve probability accurate enough? So we're going to go to our applet. So I go to one proportion, and I need to type in my numbers. So I have a 0.21 population proportion, and I need to do each of the sample sizes. So if I put in a sample size of 20, I do 10,000 draws, and I draw my samples. Let's hide those spinners. Okay, it won't let me, but so we did our probability of success, our sample size, our number of samples. Let's say we want to get a proportion of successes. We said at least 0.35, so 0.35 or more. And we'll click count. Okay. And you'll see that my simulated probability is 0.1065. Now, when I did this to make your notes, I got a simulated probability of 0.1040. Okay, my simulated probability 0.1040. Just fine. We expect a little bit of difference for each time we simulate it. Okay. If I want to do the theory-based normal, if I want to use the normal curve and get a theory-based p-value, I just click the normal approximation. I don't have to do anything else. And you can see that that theory-based p-value is 0.0621. Okay. That stays the same every time because there's no simulation. It's actually just using all formulas. Okay. Just looking at the graph, you can see the 0.35 or over. Yeah, that's a pretty big area. Like, there's about a 10% chance that I could get a sample proportion of 0.35 or more when I have a sample size of 20. But coming back to it, let's try our different sample sizes. So if I change it to a sample size of 40 and read the process, now my p-value goes to 0.0294. And you can see just looking at the picture that my whole distribution shrank a bit. My standard deviation got smaller. I have a much smaller tail here, and my p-value is now only 0.0294. And my theory-based one is 0.0149. Okay. For sample size of 75, my scale keeps changing, so it doesn't really seem like it changed, but it's because my scale changed. Now I have like a really small tail. My p-value is really small at 0.0014. My theory base is 0.0015. But at 400, notice it's almost impossible to get a sample proportion of 0.35. Okay, it's so far out there, my p-value is just approximately 0. Okay, and same thing for the theory-based p-value. Now, if you remember, what were we actually looking at? We're trying to say, for what sample sizes is our theory-based normal curve probability accurate enough? Now, whether or not it's accurate enough might depend on how accurate you personally want to be. But if I look at these, starting at the bottom, at a sample size of 400, notice they're like almost identical. Okay. And 0.014, 0.0015, again, like almost identical. No one's really going to care if you're that far off. Okay. But once you get up to 40, we're at 0.029 or 0.0149. This one's like twice as big as this one. That's a big difference. Okay, or here we're a difference between like 6% or 10%. Again, that's a big difference. So for which of these sample sizes would you think the theory-based p-value is good enough? For 20, I would say no. Okay, that one is not good enough. That's a big difference. Okay. For 40, again, I would say no. I don't think that we should be using the theory-based p-value. Okay. But for 75 and 100, sure, those look great. Now, this isn't a coincidence. Let's look back up to what we did on the previous page. Do you remember? Sample size of 20, we said we shouldn't use the p-value. Sample size of 40, we said we shouldn't use the theory-based p-value. But for 75 and a 400, we said, yeah, sure, the theory-based results will be accurate. That's exactly what we saw when we actually did the simulations, which is pretty cool, right? Okay, so the theory-based does not work for a sample size n equals 20 or n equals 40, okay, which is what we figured out on the previous page. So just cool to see that it actually does work like that, okay? And just so you have it of your notes, here's what it looked like when I did the theory-based p-value, because I just want to remind you, you can always do the simulations, but if you only cared about the theory-based, you could just put in the 0.21, you can put in the sample size, you can say count for as extreme as 0.35, you click normal approximation, it will tell you this is your theory-based p-value. And it will even draw the normal curve. There's no simulations behind it because I didn't do the simulations. Okay, this is now like my theory-based p-value. Okay, if you click the summary statistics, it will tell you the theory-based mean and SD, just in case you wanted to find those. Let's see, let's review just a little bit more. So continuing the Douglas example with pi equals 0.21, let's suppose we want to take a sample of 200 voters and we want to use the count as a statistic. So we did proportions, but what if we wanted to use the count? Okay, so what would be a better label for the horizontal axis? It would probably be something like the number of successes. How about like the number of successes in each of the different samples? Okay, well, let's see, where is the center? It's probably about this, like 16-ish, maybe. Let's see if we can figure out what we would expect. So I'd probably expect my population proportion is 0.21, so I'd expect like 0.21 times 200, which gives me 42. Sorry, I forgot. I accidentally changed this to 75. When I made your graph, this is supposed to be a sample size of 75. So when we do the center, it's supposed to be 0.21 of 75. So 0.21 times 75 gives me 15.75. So that's what we would expect if we look at the simulation. The mean equals 15.758. Okay, so that matches kind of what we would just naturally expect. Again, if you don't remember how to do these formulas on the exam, you can just use the applet. It will tell you the mean and standard deviation. And what is the shape of the sampling distribution? Well, it looks pretty normal to me. And what is the standard deviation? I haven't given you a formula for counts, and I'm not going to give you a formula for the counts. You can just use the applet, and it tells you 3.524. Okay, is going to be your SD. So it works very much like proportions, because remember the proportions and counts, they're telling us the exact same thing. So if you looked at counts, you can still find the center. The shape is just going to be normal, and the applet will tell you the SD. Okay. So here's a remark. We mentioned this earlier. The sampling distribution is what we'd expect from all the possible sample proportions when we know the population parameter pi. When we're doing a statistical test, though, and we just have a hypothesized value of pi, we don't actually know what pi is, the book calls it the null distribution instead, because it's the sampling distribution of all the possible sample proportions if the null is true. So they just kind of gave it a new name. Basically, sampling distributions, the null distribution, they're the exact same thing. You might even see us accidentally use them interchangeably. Don't worry about it. They just mean the same thing. The null distribution is just because we're doing hypothesis tests and we're assuming that the null is true. Okay, one more example. One politician claimed that 45% of Americans had at least one of their grandparents born outside the United States. One statistician thought that that was too high. As part of the General Social Survey in 2018, a random sample of U.S. adults reported that 881 out of 214 said yes, at least one grandparent was born outside the United States. So first of all, what is the parameter here? That would be the proportion of all U.S. adults with at least one grandparent born outside the U.S. Now, that's it in words. Do you actually know what the value is? Could you write it out with symbols and words? Did it ever tell you what it is? We have a claim, but that's just a claim. We don't know the true value, so we'll just put a question mark. I don't know what my population proportion is. The statistic would be the proportion of the U.S. adults in the sample with at least one grandparent born. So proportion of U.S. adults in the sample with at least one grandparent born outside the U.S. And we'll call that P hat. It did tell me the numbers for that. It actually gave me the counts, but we can do 881 out of 2,214. And if we divide that, we get 0.398. Do you consider that this sample of 2,214 U.S. adults, would that be generalizable to the over 23 million U.S. adults in 2018? Well, think about it. For it to be generalizable, we need to have our sampling frame be the entire population. So we need to see, like, did they actually use the entire population when they check the sample, or did they only look at people in Utah, or only look at people in nursing homes, etc.? Okay, but it doesn't really say specifically. It just says a random sample of U.S. adults, so it sounds like it probably is the correct sampling frame. It says it's a random sample, so I would say yes, it's a random sample. Let's see, supposing the claim is true. When I say the claim is true, that means we're going to suppose that pi equals 0.45. Supposing. What do you predict for the behavior of the distribution of sample proportions? Or like, what do you predict for the sampling distribution? The shape should be, well, is our sample size big enough that it should be normal? Do you have at least 10 people that said yes and at least 10 that said no? So 881 said yes, and if you want to figure that out, we could do 2214 minus 881. So 1,333 said no. Okay, so is that big enough? Yes, so it should be normal. They're both at least 10. My mean should be equal to just pi equals 0.45. So my mean of my p hat should be equal to pi, so 0.45. And my standard deviation of my p hat should be equal to the square root of pi times 1 minus pi all over n. Okay. So this would be the square root of pi equals 0.45 times 1 minus 0.45 all over a sample size of 2214, which get 0.0105. Let's see, so now let's actually do a test. So let's write out the null hypothesis. Okay, you can write it out in words, you can write it out with symbols. Okay, the null hypothesis, okay, so remember, or maybe do the alternative first. So they want to show that 45% is too high. So he's actually hoping to show the alternative hypothesis that pi is less than 0.45. Or he's hoping to show that the population proportion of all the U.S. adults with at least one grandparent born outside the U.S. is actually less than 45%. The alternative hypothesis then always has to be an equals, so it will just be that pi equals 0.45. Is the sample size large enough to use the theory-based approach? Well, coming back up here, we checked both of my successes and failures are at least 10, so yes. And now, for a p-value, we need to go find the applet. So my probability of success, we're assuming the null hypothesis is true. So we're assuming that it's 0.45. We don't know that, we're just assuming. Let's see, 2214 is my sample size. Let's draw 10,000 samples. Okay, now I can click the summary statistics here. You'll notice, oh, my mean, that's really high. That's not what I was expecting. Oh, because it's on the number of successes, not the proportion. Okay, so now my mean is 0.45. That's exactly what I predicted up here on number 4. My SD is 0.011. Okay, 0.01. So that's just off a bit by rounding because, again, it's a simulation, but about what I predicted. Okay, now I need to count my samples. What am I comparing it to? My sample proportion is 0.398. So we want to compare it to 0.398. Okay. Do I want, oh wait, I didn't want everything greater than 0.398. Okay. We said a less than. We're looking for evidence that it's less than. So I changed that to a less than. And so it's saying if you have a sample size of over 2,000, the chance that you'd get a sample proportion 0.398 or less is about 0. Okay. It's big enough I could use the normal approximation. So again, my p-value is about 0. Okay. So it's about 0. So definitely evidence against the null. Okay, so that means we have evidence for the alternative. But my conclusion is always in terms of the alternative hypothesis, because that's what my boss wants to know. So we'd say we have very, very strong evidence. There's a very, very small p-value. So very strong evidence that the proportion, or that less than 45% of all U.S. adults have at least one grandparent born outside the U.S. Now, just as another thing, do you have any reason to suspect that the respondents could be giving misleading information to this question? What are the implications of your answer? So if you think about this, like maybe, and I'm not saying they are, I mean, I wouldn't have this issue, but maybe some are embarrassed to admit yes. So we might be underestimating. Of course, you might have the flip side. Maybe some people actually wish that their grandparents were born outside the U.S. Maybe they said that they did, but I would bet probably more, maybe like they didn't want to admit it, so we were underestimating. So that's just that bias that we talked about. This is a non-sampling bias. If they're embarrassed, that's non-sampling bias. It's not how we picked our sample. It's just that they didn't want to answer. Okay, and you can see just how we put it in for your notes. My population proportion under my null hypothesis 0.45, sample size, number of simulations. I did proportion successes. I did as extreme as going to the 0.3979. Here's my normal approximation.